Let's focus on this stuff for now. Extended Hückel theory. We ran into problems with Hückel theory because what can it only accomplish? Planar systems and p orbitals. What about stuff that's not planar or has more orbitals? How do we deal with that? Yeah, we can apply it further. We were starting to talk about how does it work. And then Joe pointed out the very first thing, we separated core and valence electrons. Core electrons. Yeah, I don't know what it'll be yet. Maybe. We'll see how far we get. Okay. From the core, separate the core from the core. There we go. Okay, so we separate those two things out from one another. This allows us to just sort of quickly not have to worry a ton about the core electrons, and we can worry about the valence electrons. The next thing we're going to do is we're just going to consider the valence electrons, and their energy is the sum of one electron Hamiltonians. So the valence electrons, Hamiltonian is taken as a sum of one electron Hamiltonians. So we can sort of represent it. Electrons. So this is meant to be valence electrons, equivalent to a summation of I. I'm going to call this H effective I, like that. 3 are guesses, or guessed wave functions, MOs. Guess wave functions. We're going to approximate with LCAO. So if that's our MO or our guess wave function, we're going to say, we'll use this notation. Our that is meant to be a comma I. Sorry, like that. Effective. Okay. So these are our basis functions. This is the contribution of the basis function to our guess or our MO. In Hückel theory, what was the only basis function we had? Yep, 2p's. We're going to add more basis functions. So unlike Hückel theory, basis functions are comprised of more than just p orbitals. Example, carbon. If you wanted to represent the valence electrons of carbon, what atomic orbitals would you use? Yep, 1, 2s. How many 2p's? Yep. Oh wait, how many? 4. So, remember quantum numbers with these guys? The 1s is a core electron. We don't care about core electrons. So now we only have this shell and this shell to deal with. 2s. We have 1, 2s because it's in the valence. Remember, each orbital can occupy 2 electrons, we're saying here.
Oh.
Yeah. And how many p's? No. No. 3.
Why?
Yep. Remember, n is equal to 2. What are the possible values of L we could have? 2. Oh, not 2. 1 and 0. 1 means P. 0 means S. ML. If we have that guy, positive 1. If we have this one, ML is equal to 0. So we have 3 different p orbitals available. If we're talking about S, we only have 1 S available.
Oh.
Bringing you back to Gen Chem. Ooh, bless. Yeah, that's all right. Oh, like, yeah, like if you're, how many electrons are occupying it? Yeah. So you need all of these guys. Okay, what about a hydrogen?
0.
Yep, 1, 1s, because we're talking about its valence shell. What about, let's go with manganese. Manganese, Mn. Manganese. Manganese? Manganese. Sorry, I already sound nasally enough. I don't need to add more syllables to make it worse. Mn. Okay, what do we got there for its valence shell? Not 3s.
Oh, 4.
Yeah. 1, 4s.
And then 5D.
Yep, 5, 3d. And yeah, we got p's. How many p's? 3, 4 p's. Yep. Because those are available.
I see what you mean.
Based upon its quantum numbers. So we would use that.
How do we get them? Yeah, how do we get them?
So even though they're not occupied, these still exist. Because remember, if we have an n is equal to 4, we have 3, 2, 1, 0 that's available. Okay? Bringing you back to Gen Chem. It's painful, I know. Oh, nah.
Yeah, see, this class should be taken beforehand.
Yeah. Yeah, that'd be great. They can't even do fractions right now, so.
Yeah, but they're still learning quantum.
They will be getting quantum numbers. Eventually they'll need it. Okay. Oh, Chem 100. Chem 100, we'll worry about that later. It's taught from an atoms first approach because we're trying not to focus on the math there. In Gen Chem, we focus on the math first because if you can't do the math, then you can't. Yeah. Okay, I guess this is actually number 4. Maybe it's kind of wrapped into number 3. The atomic orbitals are Slater type orbitals.
Oh my god, I watched YouTube video on this.
Did you? Cool. Who was talking about STOs?
Was the guy?
Yeah.
Oh, I know.
Okay. So STOs are very nice, but they're sometimes hard to program. There's some programs that utilize it. For the basis function depends on these things. R, theta, phi. We also got this capital, I think it's eta. Yeah, which I'm really bad at drawing, I'm sorry. N, L. I can do it good once per class. That's my good one. I'm done. It's over after this. Okay. So if you see something that just looks like a scribble, that's what it is. It's a factorial. Yeah. Yep, you probably happily or unhappily remember these.
I just remember.
I need more space. This is actually PChem too. I'm just going to mention it for a couple different reasons. M sub L. Katie, have you gotten to spherical harmonics yet? Okay, that's a fancy function related to spherical harmonics. Yep. Now, looking at this, does that look like something fun you want to do by hand? No. So that is why it took so long to be able to do this sort of stuff, just because of the mathematical complexity associated with it. No, that's what our basis functions look like. This term, I don't really want to talk about it much, but there's something else more in there. Okay?
Those are twos, correct?
These are twos. They are not partials. They're actually the number two.
Are we going fully in depth?
No. Nope, we don't have enough time.
It could actually be entire.
Yes, they can. Yeah, they could be a multiple long lecture, and we do that sometimes in PChem. The other aspect is you talk about like the program Gaussian uses Gaussian type orbitals versus Slater type orbitals. There's a difference there in terms of what you can do computationally, and I just don't want to touch that right now. No, I just use the stuff. I don't develop any of it. I mean, yeah, so I need to know what's going on there. So my research utilizes it. Let's put it that way. I don't develop it. Okay. So now, if we use our one electron, I guess this is step 4. We use our one electron Hamiltonians, and they follow this eigenfunction eigenvalue equation. Remember, what is this thing? Yep, effective Hamiltonian. What does the Hamiltonian get you? When it acts upon a wave function, what does it spit out? Energy. Yep. This is our guess function, our MO. What these things are is the energy corresponding to our one electron orbital. Okay. If we wanted to get the total energy of our system, we're going to put E total. How can we relate it to these epsilons, these little e's? Yeah, I'd sum them up. We could do that. Okay. But we don't know, what things don't we know here? Right. We have the guess function, but we don't know those coefficients, right? And do we know this thing? No, we don't know the E. What type of energy do we want? We want kinetic and potential. What do we want to assure when we like put all this stuff in? What do we want to know about our energy? Yeah, that'll be important. Trying to ask this without saying the word directly. In the past, we have had guessed wave functions, and we wanted to make sure
Oh, we want the minimum.
we want the minimum energy out using the variational principle. So what do you think we're going to have to do? Mhm. Yep. So we're going to set up a secular determinant. So we want to minimize, oops, what I just erased, that energy, utilizing a secular determinant. So we set up okay. H11 minus what? Yep, E. And we're going to use little epsilon E for our guess times what? Yep, S11. This is what type of integral again? We did use a delta function for Hückel theory. We're not going to do that here. But what is this integral called? The what integral? Starts with an O. Nope, not orthonormal, even though it kind of is orthonormal. Actually, no, it's not orthonormal. Oh, overlap integral. It's the overlap integral. It lets you know how much the basis functions overlap. This guy's known sometimes as the resonance integral. H12, da 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 da. Then we go all the way till we fulfill our requirements, and so on. Do we need to do the second ones, or can I just put dot dot dots to the end? Okay. Right. Wait, it means worldly. There is a reason for it, but I don't actually remember why it has that name. Devin, do you remember why the secular equations are called the secular equations? I don't know either. I knew at one point there's a historical reason for it. Yeah. Probably something related to that. Yeah, exactly. Yeah. They wanted to be God. They didn't want to let the determinant determine everything. But there is a reason for it.
So because they are used in mathematics, particularly in celestial mechanics, to calculate long-term slow changes in planetary orbits.
Oh, okay. So it all has to do with planetary orbits?
I don't know.
That's okay. That's interesting. Ha! That was a good one. You got to teach Pete Schneid how to tell jokes. Okay. Yeah, I hope he does. Okay. Oh, I forgot to say, what's this whole thing equal to? 0. Okay. Okay, so Katie, you said, oh, these are delta functions. Life's okay. That's what it is in Hückel theory. In extended Hückel theory, not the case. So, however, in extended Hückel theory, Sij does not equal a delta function. Oops. Yeah. I can't have you do this on an exam. You need a computer. You could do it. You might be able to do it for a simple like H2 or something, but you need a computer.
Like a good computer, or
no? I mean, they were doing this back in the 70s with a differential analyzer. In some cases, rolled head punch cards and was doing it that way. So, okay, HII. So we have IJ terms, which we'll talk about what the IJ terms are, but the II, so the ones along the diagonal, they come from experiment. And depend on the atomic orbital. So that's sometimes where you hear semi-empirical Hückel theory or extended Hückel theory or just E-Hückel theory. There's some parts that come from experiment. So for example, if you were to look at this evaluation, for you guys who are not in quantum, this is the same thing as like psi star psi d tau. It's just a shorthand. It's known as Brock-Ket notation or Dirac notation. It means the same thing. Don't really worry about it. What that value would be, negative 20.8 electron volts for like carbon 2p. It changes again, negative 11.3. Okay, so we sort of explained what this thing is. We've explained what these guys are, but what about the off diagonals, the HIJs? We can't approximate them to just be a 0 and go away. I know. The off diagonal. Elements. Hij, as suggested by Wolfsburg and Helmholtz in 1952. So these were the original developers of extended Hückel theory. Said that you should try to use this equation. Where K is just a constant. So you basically, you plug in numbers for, oops, I'm sorry, this should be a JJ. You look at the atomic orbitals that you're considering, you add these two energies together, you look at their overlap because we're using Slater type orbitals, and you can calculate the overlap from those pretty easily, relatively easily. And you're sort of just taking an average of those values. Where K is usually 1.75. K is kind of just a number. It changes based upon the system of interest that you're looking at, and you just kind of guess it. You pick it. Okay. Now, what is this going to do after we solve this thing? Yep, we get energies. So now, what step are we on? 5? 5. We get energies. That tells us number of these guys. And then using the secular equation, we can start to get those coefficients. So just like we did with Hückel theory. Okay, like I said, this becomes more mathematically complex, but your computer can do it in literally seconds, which is nice. Avogadro can do this very easily. A lot of the other programs I utilize, you actually use this as a first guess before applying other quantum mechanical methods. So it's a pretty good first guess, at least for the electronic structure. We're going to be utilizing this when we talk about surfaces and considering overlap between orbitals as we go to extended solids. Okay. All right, we got 10 minutes.